Welcome to this short demo of the patient level prediction package. You can find the package on GitHub on the link described in this slide. This package has been developed within the patient level prediction workgroup, which is led by me and Jenna Reps within the Odyssey community. The patient level prediction package runs against the OMOP common data model. This model is described in a lot of detail on the odyssey.org website, and there are other tutorials there if you want more information. What we like to achieve with the OMOP common data model and its vocabularies is to obtain both syntactic and semantic operability. We want to obtain a common underlying data structure for all the databases that we want to use in our research. We also want to speak the same language, meaning that we want to have a common vocabulary, a standard vocabulary that has been developed in Odyssey as well. The nice thing of this standardization is that this would allow us to run common tools and standardized tools against the common data model and the vocabularies. And this would allow us to do very fast and very efficient research. And most of all, we want to do a transparent research, meaning that we want to be fully reproducible in the pipeline. The patient level prediction workgroup has been started to do this in the area of patient level prediction. And there is a wiki page if you want to know more about this workgroup, or even better, if you want to join our team. The overall objective of the workgroup is to establish a standardized process for developing accurate and well-calibrated patient-centric predictive models. And we want to utilize this for multiple outcomes, and we want to apply that on as many databases as possible. So meaning databases that have been mapped to the OMOP common data model and the vocabularies. Within the workgroup, a second version has been developed of the patient level prediction R package. And Jenna Reps is going to demo this package in this video.
So the code is available on GitHub. If you actually want to look at all the different R bits and the sections, you can actually go to this link. Otherwise, you just want to actually look at the document that I'm going to be showing, which tells you all the instructions of how to install it in R. So to run this, you need R. You also need to have Java and Python for some of the methods. So I'll go through that and show how we actually kind of suggesting you install those as well. Because Python can be quite a pain to install in Windows. So luckily we found, Martijn found a nice easy way to get Python on, which doesn't require taking a day or two to install Python like it did for me. So this is the link if you're interested. You need the R. I always recommend having the latest R. We've got that you need R 3.22. I'm not sure if that's the latest. This is there's pretty a later one there, so it's pretty just worth getting the latest one. You need to have R tools to actually install the GitHub packages that we've got, and you'll need Java and Python. So the Python installation that we're recommending is we're suggesting Python 2.7, and we're suggesting use Anaconda because that will actually install the Python and all the packages in Python that you need for running the prediction models nicely. If you don't use Anaconda, then you have to do a lot of extra setup yourself, which isn't very friendly. So then if you want to install our actual package, the first thing you need to do is install DevTools in R. So once you've got R, just run install.packages DevTools. Then you load the library DevTools, and that means you can then install packages from GitHub. So once you've got DevTool loaded, you can then install the SQL render, database connector, Cyclops feature extraction, and patient level prediction. Actually, I think now Cyclops can be done just through install.packages. So that's actually something that you can kind of choose whether you want to use the Odyssey or the install.packages. So these are the things that you need before you get patient level prediction. Once you've run all of this code, which you can get from our PDF that we've got online, and just copy and paste this. Once you've got this, then you can actually run our package, and it should be working. So the example is at this link here. So if you go into our GitHub, then you can actually kind of go through the files and you can get the building predictive models. To do a prediction model through R, the first things that you'll need to do is you'll need to create a target population. So you need to define your target population, you need to define your outcome, and then you need to kind of define the time period that you're going to be looking for the outcome for doing the prediction. We generally use that in Atlas but you can do this with SQL as well. Again, this is in the document how you actually do this and what it's needed. I'm going to be showing you it through the Atlas example. So I'm just going to go through now to the code that we've got. So this is actually what the document is here. So you can see it's quite an extensive document. It's got a lot of information in there. It tells you how to do the installation, tells you how to do the data extraction step by step, how to use Atlas, how to create your own code here. Let's actually see it all running. So I've already installed the patient level prediction. So generally you'd need to run this. If you need to uncomment this and run it all, and it should just install it. I've already done that, so I'm going to skip that section. Then you want to actually load the libraries as the standard way in R, so you just want to run all of these, and then now you've got the patient level prediction loaded. The main thing you need to do is you need to have a connection set up. So this will be using the database connector. Again, all of this code is in the PDF document, so you can just cut and paste from that PDF and then put in your actual details. So with the database connection, you need to put in the type of SQL you're actually using in your database management system. So I'm using Power Data Warehouse, but there's various different types you can use here. I'm sure if we put question mark here, you can actually see the different types that we support. So at the moment we've got support for MySQL, Oracle, Postgres, Amazon Redshift, SQL Server, Power Data Warehouse. So these are kind of all the ones you want to enter depending on what your database is. Then you want to put in your server details, your port, your username and your password. That will then give you a connection. So I've got these set up as system, environmental variables, so it actually stays hidden. But I can set up and run this now, and it will give me a connection. So now this is actually the details that will let me connect. So I could connect to a database using this now. So if I think I put connection equals database connector. If I put this, it will now give me a connection to the SQL server. So now this is a way of connecting to the CDM database. You also want to put your schema, so the actual database that your CDM database is in. So I've called an environmental variable called CCAE, which is just the name for the CCAE database that we've got. And you also need your CDM version, so whether you've got 4 or 5. Generally at the moment we mostly just support 5, I believe. I'm not sure if it will work for 4 for some of the features. When you're doing the prediction, you need to also say what variables you're going to be using for the prediction. So we have in the feature extraction, which is this library here, we actually have a function that creates or defines what features you're going to be using. It's quite a big function. So in this one, you can actually say whether you're going to be using demographics, and if you're using demographics, whether you want to use gender, race, ethnicity, age, month, year. So if you put false here, if you put true for gender, it will still actually come as false. So this is kind of like a hierarchical code. So if you're saying that you're not using demographics, even if you say use demographics gender, it won't use it because you said here you don't want to use demographics. So if you want to use gender, race, ethnicity, you need to make sure this is true. And this is the same for things like use covariate condition occurrence. If you put covariate condition occurrence equals false, even if you put the occurrence of 365 days as true, it's not going to actually use that. So you need to make sure this is put as true if any of these are put as true. But in here you can see like it goes through all the different variables that we have in the CDM. So we've got the demographics, we've got the conditions, and we look at different time periods. You can look at 360 days before your index date. You could look at 30 days before your index date. You can look at any time. So I think this use covariate condition error ever. And you see that this all kind of refers to different tables in the CDM as well. So you've got the condition error table, and you've got the condition occurrence table. You've got the drug table down here, so drug exposure. You've got procedures, observations, measurements. So these are really extracted from the different CDM databases, tables, and then you can also say you can use groupings. So the groupings will actually use the hierarchy that we have, the vocab hierarchy that we have, to actually combine the children together into kind of a parent grouping using like SNOMED or MEDRA. So there's quite a lot of options here for what features you want to use into your prediction model. And this is something that you probably want to spend some time playing around with and picking which ones you want. There's also some smarter, so rather than just using individual concept IDs with like some basic time periods, we've also got things where you can use risk scores. So there's some risk scores already calculated in, like the CHADS2 score or the DCSI score. So these will actually be automatically calculated score, and it will use the conditions that people have prior to their target index date to determine these scores. You can also say you want certain concepts excluded. So you can say in this exclude covariant concept IDs, you can list certain concepts IDs that you don't want included as predictors. And you can also specify things that you only want to include. So if you put here, it will kind of force them in. You can also get rid of covariates that aren't very common. So if you select that you want all the conditions, but you then put delete covariate small count is 100, it will get rid of any of the condition concepts that get brought in from this that only have, say, 99 or less people who have the condition in your data set. So if you've got a very small data set, you might need to adjust this. For example, if you only were doing a prediction for 1,000 people, if you're saying that you want 100 people to have the variable, then that might actually mean that you end up with very few variables. So this often will be adjusted depending on the size of the data set you have. But for example here, I've just said that we're going to use the demographics, we're going to use gender and age, and we're going to use condition occurrence, and we're going to look at condition error and whether they ever have it. And we're also going to look at kind of a group. We're also going to look at drug exposure and also, again, the drug error. So, and then we're going to ignore any of the variables that occur less than 100 people. So if I run this now, this will give us our covariate setting object. Then the main thing is actually getting the data. So a lot of people, when they're doing machine learning, they automatically think that the data is going to be in this nice, maybe CSV format where the rows are your people or your things and the columns are your features. We don't have that. We have our data in the electronic health kind of record format or the CDM format. So we have for each person time-stamped events, time-stamped conditions and drugs, procedures, measurements that they have, and then all of these in separate tables. We don't have this nicely formatted data. So this get PLP data is effectively a way of us to process from our CDM CDM format into a nice data set that our machine learning algorithms can then be applied to. And for every prediction, you need to have your target defines, so who it is you want to do your prediction for. Your outcome defines what it is you're trying to predict, and then you also will later on need to specify when it is you're trying to do this prediction period for and such. So in this case, the get PLP data, we're going to be putting the information to connect to our database. We're also going to be putting in details about our target population. So in this case, this is where you have the cohort ID here. So within the cohort table, which we created using Atlas in general. So I don't know if many of you have seen Atlas or used Atlas, but Atlas is an interface that we have developed in OMOP and Odyssey, where you can create different cohorts, or there's some people don't like the term cohort, so if you say it's a way of defining a certain subpopulation based on some sort of attribute. So here we're looking at people who have a drug exposure of antidepressants during 2011. They have to be older than 16. We're looking at that they have to have at least 365 days observation prior to the antidepressant. And we're looking at all the times that all the antidepressant prescriptions that satisfy these conditions. And then within them, we're making sure that they don't have any antidepressants or antipsychotics in the year before, or any time before. They didn't have psychosis, mania, dementia before, but they must have had a depression either 180 days before to 30 days after. So this here is a way of us defining some population. When we run this, it's going to give us what we call a cohort, but as I said, is probably actually better just thinking of it as a population. And this is now linking here. So if we look at this, we've actually got this number here. This is our ID for this population, and we plug this in here saying, okay, these are the people we want to do the prediction within. And then we do a similar sort of process for our outcome. So I think I've picked stroke. Yeah, so right here I've picked an outcome of stroke, and it's going to be defined in this way, again using the Atlas tool, but you can create this using SQL without using Atlas if you wanted, and that's, again, it's in the document. And then again, this gives us our ID here, which will be referred to here. So you need to say your outcome ID. Once you put this in, you can then run this code. I'm not going to run it because it takes about 10 minutes, or it depends on the size of the data, but it can take up to hours if you've got a very big database and your cohorts are very big. So if your target population is very large, then this could actually take quite a long time because you're actually running quite a lot of SQL in the background to get this data. But the object you'll get is what we call a PLP data. So I've already extracted this, and in the PLP data you end up with a cohort which tells you each person that you're actually doing the prediction for. So this is your target population. So you've got some identification, which is the row ID, the subject ID, which is an identification, but you could actually have multiple subjects in your cohort. So you might find that your target population could consist of any prescription of antidepressant that satisfies the criteria. That actually means that the same subject could be in twice at different time periods, so they just have a different start date. So the row ID is unique, the subject ID isn't necessarily unique. Then you have the ID for the cohort, which is the same as what you've got here. You've got their cohort start date, so this is the date that you're going to be kind of looking at your prediction relative to. So prior to this date is what you're going to be using to extract variables, and after some point after this date is what you're going to be looking at to see if you can predict the outcome occurring. And then we just have some information like how long were they observed before their start date, how long were they observed after this date in the database. So this just tells you some information here, because generally if someone's only observed for say a day before they're in the cohort, they're probably not going to be useful because they have no information that you can use to extract variables. So we're probably going to remove them. So this will kind of get used in the next step when we're actually seeing who's going to be useful for our data, for our prediction. You also have information about who has the outcome. So we've got the people who have the outcome here. And again, you have the row ID matches up to the cohort. So the outcome row ID and the cohort row ID, if you have an ID of one, that's the same person. So this is the unique identification. And you have the outcome ID. You can actually, here I've just put one outcome. You can put multiple outcomes in one extraction. So if you've got, if you're looking at the same target population, but you want to look at 10 different outcomes, you can put 10 different outcomes here by just putting them into an R vector. So here, if we wanted to look at outcome that was referred to as 2394, an outcome that was referred to as 79, and an outcome that was referred to as this big number, then you could put this here, and this would then, in the PLP outcome table, you just have outcome IDs for 3 different outcomes. And you also, it tells you how many days to the event. So this will actually tell you relative to the cohort start date for the row ID. So here, this person actually had the outcome before their cohort. So you might say exclude people if they have the outcome prior. So anyone with a negative number will just get excluded from the data set. Then we have information about the covariate. So this links up to the covariate settings that you select. So here you get the row ID, so this tells you the person, the covariate ID. So this is telling you what covariate they have, and then the value. So this is saying that they had covariate ID 13. And we can look up what covariate ID 13 is using the covariate reference. So this actually just tells you the covariate ID 13 is age group 15 to 19. And then you also have an analysis ID that kind of links to it. So analysis ID 14, I believe, is demographics. So earlier on we selected we wanted demographics and we wanted age. So we've got analysis ID 4 has come up for that. And then the covariate 13 is its age. So whoever person row ID 2 was, their age 15 to 19. So this is the PLP object, and then you also just have a metadata which just tells you about how you've extracted the data. So this tells you the SQL that was applied, the call that was done as any deleted covariate. So some of the covariates might be redundant. For example, you don't want both genders in your data set. If you know someone's male, then they're not going to be female, and vice versa. And also, if you don't want all the ages, because one of the age groups is going to be redundant. So you can see which gender and which age got deleted here in this bit here. Now, this has got you the people who have. It's got your target population. It's got your outcomes relative to the target population, and it's got you the covariates before the person's in the target group. So before this cohort start date, you created these covariates, but you still haven't actually defined when you want to do the prediction. Just noting here, you can save your PLP data if you want to. To save your PLP data, you just run save PLP data, put your PLP data object, and you put in the location you want it saved to. But to actually, if you want to, when you're doing the prediction, you need to say when it is. This is done using what we've called a create study population. So if you run the create study population, you put in your PLP data, you say which outcome it is you want to do the prediction for, because as I mentioned before, you can actually put multiple outcomes into your PLP data. If you've only got one outcome in your PLP data, then it's not too important. But if you've got lots of outcomes, you need to say which one you're actually going to be focusing on. And then you've got various parameters that are going to define your prediction problem. So include all outcomes means, do you want to include people who have the outcome but maybe leave the study shortly after, so they're not observed for the whole study period after. So for example, if you want to do a prediction, I'm going to predict stroke within 5 years. Someone has a stroke and then they leave the database for some reason, so they're not observed for the whole 5 years. Do you still want them in your data set? If it means something that's going to like maybe increase your chance of death, an outcome that's likely to be linked to death, means that people, if they have the outcome, then they might not be observed the whole time. So if you exclude them because they're not observed for the whole period that you're doing the prediction for, you might actually ignore quite a lot of your outcomes. So this is here just to make sure that people are included if they have the outcome you're interested, even if they're not observed the whole time. And by default, this is true. But if you don't want that to be true, then you can put false here. And then you can say whether you want the first exposure only. So if someone's had the outcome prior, or if someone has the outcome before, or sometime, or if they have it, I guess, in two times, you can actually include them twice. It's because we saw the subject ID can come up twice, even though the row ID is unique. So do you only want to include you on the subject IDs to be unique or not for the outcomes? The washout period is what we mean to say the minimum number of days they must have been observed prior to their cohort start date, so that the date that they're in the target group, and they're kind of doing the prediction relative to how many days do you want them to be observed if they're in the data set. Generally, we're going to say we want at least a year's observation beforehand, because this is what we're using to create the variables. If this isn't very long, then we're not going to, although variables are pretty going to be quite noisy, you don't know if they've actually had things that you just don't know about. The bigger the washout period, though, obviously the longer you've observed them in the data set prior to their cohort inclusion. So you're probably going to have nicer features, nicer variables. You can also remove people if they have the outcome prior to their prediction date. So if you want to remove people who've had the outcome before. Maybe you're looking at the first time stroke and you're saying if someone's had stroke before, we don't want them in the prediction, then you can say remove people who have it, and then this tells you how far back you look. So at the moment we're removing people who have stroke in the past year. You could put this to 9,999 and pretty much remove anyone who's ever had the outcome. And then the last little bit is actually saying when it is you're trying to do the prediction. So this is relative to the cohort date that we have here. So for each person in the cohort, we have their cohort start date. We're going to say we're going to look at the prediction from the cohort start date plus 1. It's going to be when we're looking for the outcome, and the cohort end date is going to be the cohort start date plus the risk window end. So we're basically looking at a year from their cohort start date, whether they're going to have stroke. So this risk window start, risk window end, this defines the time period that you're actually looking for the outcome. So, and then here also I said that I want them to have at least 364 days of observation. So I'm saying here that I wanted them observed for the whole risk period, unless they have the outcome, because we're including all outcomes. So this is a little bit, there's quite a lot to take in here, and it's pretty recommended to look at our example PDF to get a better idea, because there's some nicer pictures there, and play around with it a bit to kind of get it, because there's quite a lot of terms here that it's hard to explain it in quite a quick period of time. So if we run this now, it's going to create our population, and I'll show you what that actually returns. So let's just look at the first 10 rows. So we see here we have the row ID, we have the subject ID, the cohort ID is all going to be the same, we have their start date, and then we have the data from observation data. So this is the same as we have from the cohort, but this time we've got an extra column where we say whether they had the outcome. So none of these had the outcome. We have their time at risk, so how long they're actually at risk, and because I said here the minimum time at risk is 364 days, again you've got people who have greater than that. The days to event is NA because they didn't have the outcome, and the survival time is the time at risk, because that's how long we're actually looking at them. You can have a look at how many people, so if we look at table population outcome count, you can actually look at how many people had the outcome. So here out of 95,000 odd people, 163 people had the stroke within the year that we looked at. So this now has actually given us our labels. So the outcome count here is basically our label for each our row ID. So this is a way of going from our raw tables really to actually classifying each person's whether they have the outcome or not in the time at risk, which is defined by these parameters here. So once we've done that, we've got our data now processed, we can just simply run our standard machine learning algorithms now. So we've got quite a few algorithms integrated into the package. Logistic regression is one of the ones that's the fastest. So to do the logistic regression, first you need to say set lasso logistic regression. This one doesn't really have, well, it has one hyperparameter, but it's automatically calculated when it runs, so you don't really actually have to input much into this one. So you can just say run this, and then we're going to run the patient level prediction, we're going to put the population in, put the PLP data in. The model settings is what we've put here, so it's going to be a lasso logistic regression. Then you need to say how you want to do the validation. So we're going to do a random internal validation, so we're going to split by person, just 25% of people are going to go into the test set, and the 75% are going to go into the train set, and we're going to do twofold cross-validation when we're doing the hyperparameter selection. So now if we run this, it's going to start running logistic regression. Because it's very quick, you can actually see it output. So when you run it, a log gets created, it tells you what PLP version you're using, it tells you, and it gives you your analysis ID for this. So this is going to be unique for every time you run a model. You get information about your cohort, about your outcome, how big your cohort was, how many covariates you've got. So here we've got about 2,000 features, or 2,000 variables being put into our model. That was the demographic, age, gender, the condition error, and the drug error. That had at least 100 people. And then we look at the population size and how many people had the outcomes. This is what I showed you in the table earlier. It's done a split 25% test, 75% train, twofold cross-validation, and it's done stratified by outcome for the split. So you make sure that 25% of the outcomes are in the test, 75% of the outcomes are in the train set. It tells you here information about the splits, tells you where the model's saved to, and now it's evaluating the model. So when you develop the model, it then automatically calculates the area under the curve for the train set, the area under the curve for the test set, the calibration information for the test and train sets, and the average precision. So this gets output here. You've got more information in this object here that gets returned, but this just gives you a nice summary about how well the model's done. So we've got an area under the curve of 0.78 on this prediction problem, so that's actually pretty good. Then we get information. We calculate information about the covariance summary as well, so you can actually see how the covariates compare between the test and train splits to see if the test and train seem to be quite good splits, or whether there seems to be differences between the test and train split. And you can also look at the covariance split between the people who have the outcome and people who don't have the outcome, so you can kind of just see some obvious covariates potentially that are predictive. So once you've got this run, this is the model's being run, and you've actually got the evaluation as well. You can now access the information. So you've got input summary here, which tells you information about how your data was extracted, how your population was created, what model settings you've done. So this information here can be used if you want to extract new data from, say, a new database, but you want the same settings. This tells you all the settings that you used for your whole process. So this is kind of saved so that you can replicate your data extraction nicely. You also have execution summary, so this will tell you information about where things are saved, how long it took to do the model, how much RAM you have, how many cores you have, information about your system and what R you're using. So this actually is more useful for us if you have any bugs. We can have a look at what is. You have your model. So the model, you can actually have the hyperparameter search here. So we all have an automatic search for the lasso, so it should just give you one row. So it tells you what variance was optimal for your, so this is the regularization value, what it was that was optimal. And it tells you basically the log likelihood, so how well it performed. You also have information about your model, so you actually have your actual model. But this isn't really all that useful for now. You have the prediction, so this will tell you your prediction for each person in here. So for row ID 1, you have this value. This is the predicted value of having the outcome. So they didn't have the outcome, they predicted quite a low value. And you have that for all the people in your data set. Covariance summary, so this is, as I was mentioning, this kind of gives you a summary about each of the covariates. So you can have a look at the covariate ID, which we saw earlier. You can have, it tells you what the covariate is, the analysis ID, and then it tells you how many people had this covariate, how many people with the outcome had the covariate. So then you can calculate the covariate mean with the outcome. You can look at the standard deviations, and you can have a look at, so it tells you summary about the people who have the outcome for the covariate, the people who don't have the outcome, the covariate, and then it tells you the test and train information. So this is just kind of a nice, simple way of comparing people who have the outcome, people who don't have the outcome, and the test and the train, and so on. And we've got some nice plots for that, which we'll see later. The analysis ref just tells you information about the names, so the ref ID. The nicest output that you get is your performance evaluation. So in here you get the general evaluation statistics. So this tells you the test and train values for your standard metrics. So you've got things like your population size, your outcome count, your area under the curve with your upper and lower bounds, or confidence intervals. You've got your Breyer score, calibration, set gradient. So this is all put here for your test and the trains. You can have a look at this. This is the reason we've got this format, is because the idea is that eventually this will get put into a database, and this seems to be the nicest format for putting it into the database. You also have a threshold summary, so this is what you can use for doing your area under the curve. It gives you 100 different points for your sensitivity, specificity kind of values. Again, you've got your test and your train combined here, so this eval will tell you whether it's referring to the test set or the train set. And you got your analysis ID, and then you have different prediction thresholds, and at that threshold, how many people were true counts, how many people were false counts, how many true positives, false true negatives, false positives, false negatives, and so on. So this is just the general statistics for 100 different points. So it's just a way of summarizing the results, but in a rather than having millions of points, we just got it down to 100 points, so that we're not going to have to save or use up a lot of space when we're saving things. We have a summary for demographics, summary for the calibration, and summary for the prediction distribution as well. So these are things that shouldn't be very big in size, but they capture everything you really need to know if you want to do a calibration plot, or you want to look at how calibrated the model is for different demographic groups. So the demographics group, for example, it shows you for a certain age group, which is age 0 to 4, that are males. You see how many people were at risk. Well, no one here actually, we didn't actually have any males over that age, because we had to say we said they had to be over 16. But here, so if I put maybe 10, we might get someone who's. Let's try to find someone that is actually. So quite a lot of the age and gender groups are missing, but you see here we've got values here that tell you the min predicted probability and the 25% range, median, 75% of people fell above or below, and so on. So this here just gives you a nice way for actually looking at, you can see basically, is there certain age and gender groups where the model doesn't do well. That's what this one does. So again, you can run the same thing. If you want to do a gradient boosted machine, you can say set gradient boosted machine. Here you've got quite a lot of hyperparameters that you can tune. So with the set gradient boosted machine, you have the number of trees that you want to do, the number of threads. Actually, that would just be the number of threads of your computer, but you can have your max depth, that's the hyperparameter, the min rows, that's the hyperparameter, your learn rate, that's the hyperparameter. So you can put in different combinations of this, and it will work out. If we put max depth equals 6,4, we put entries is 1, 10, 100, min rows of 1, 10, 20. This will look at every combination of these. So you'll look at max depth of 4, number of trees 1, min rows 1, max depth of 4, number of rows 10, min rows 1, max depth of 4, number of trees 100, min rows of 1, max depth of 6, min rows of 1. So it basically looks at every combination of these settings, and it will actually evaluate the model with that combination, look at how well it does, and then calculate the cross-validation error of the curve, do that for every combination, and then pick out the best hyperparameter combination and return that model to you. So this will actually do quite a lot of training in this situation if we ran this right now. So this is effectively, it's doing a grid search. You can do the same for random forest. If you want to see what hyperparameters random forest has, again, you can write question mark set random forest, and you have that there are m tries, n trees, max depth. And you can also do a variable importance true or false. So this is whether you want to do a pre-process step of selecting the better features, or whether you just want to use all the features when you do your model. All of the models have a seed argument, so you can actually set a seed if you want to make it so that the models are reproducible. You can put seed equals 1, and it means that every time you run the model, you'll get the same output. At the moment, we have a multi-layer perception model, but it doesn't seem to do very well, so I'm saying this is still in progress. I think there's more hyperparameters that I need to put in for people to actually play with, or it's going to be a lot slower to actually do the grid search, because you're probably going to have to do a lot bigger grid to get you some good results. Once you've got your results, you can then do save PLP result here with your result and where you want to save it. And then if you want to load it in the future, you can use load PLP result. So save PLP result, load PLP result, and you get it all back. The only thing left to show is the plot. So you can put in your performance evaluation of your like logistic regression object, and you can plot the sparse rock, and that will give you your result here of your rock curve. And you can do the calibration as well here, or you can just run everything and save it to a location by running plot PLP and put in the path where you want all the plots, and that will do various different plots. So if I go to S and plots, you get all of these that come out. So you get a demographic summary plot, you get a precision recall plot, a predicted PDF plot, a preference PDF plot, the sparse calibration plots you just saw, and the sparse rock is you just saw, and a variable scatter plot as well. So you end up with a lot of plots that you can kind of look at and look in to investigate how well the model's actually done. So that is the majority of the functionality. There are some additional bits in there as well, which you can see if you go through the example PDF. There's a demo as well, so you can do the demo, run everything. And there's a nice bit as well where we have a function called apply model, where you can extract new data, create the population using the same settings, and then put in your model, and it will evaluate your model on new data. So this is a way of doing some external validation. So this is the main code.
If you have any problems with running the package, or if you have some good ideas for new features, please post them in the issue section on the GitHub. There's also a forum that's dedicated to the work that we're doing, and the link is shown on this slide. Thank you for your attention.